So, hi, like Peter said, I'm Bethany Goldblum. I'm a research engineer in the department. It's a pleasure to be here today, and I want to thank the committee for giving me the opportunity to speak to you about my work in nuclear security science. So this is a plot that shows the global number of nuclear weapons as a function of time. And so you can see that the number of nuclear weapons worldwide peaked in the mid-1980s, but the number's been decreasing even to the present day, but it's still substantial, something like 10,000 weapons worldwide. And at the same time, the number of nuclear armed countries has continued to increase. So for the past 8 years, I've been working to reduce the risks posed by the spread of nuclear weapons and related technologies through the Nuclear Science and Security Consortium, or the NSSC. Like Peter said, the NSSC is a group of institutions, academic institutions, and national labs working together to train the next generation of nuclear security experts, supported by the National Nuclear Security Administration. And we do this through research and development in collaboration with the labs. So the NSSC is comprised of 7 universities and 5 national labs, and that's shown on the map here on the top left, including Lawrence Berkeley National Lab. So in 2016, with Professor Yasmina Vujic, I led the successful recompetition of the NSSC contract for an additional $25 million over 5 years. The NSSC engages in a broad range of research activities. And so those are listed here in this graphic. The focus areas are listed vertically, and the cross-cutting research areas are listed horizontally. So as executive director and director of education for the consortium, I've helped to place more than 100 students and postdocs into careers at the national labs. And some of them are pictured on the bottom of this slide here, which was a snapshot from an earlier time, back when we were together at the NSSC Fall Workshop, really not too long ago in October at Lawrence Livermore National Laboratory. So rather than discuss the research successes of the consortium today, of which there are many, I'm going to talk about my own independent research program, which has been largely inspired by the NSSC mission. So my research is organized around 3 main themes: applied nuclear physics, which includes experiments to determine basic nuclear physics quantities; data analytics, with a current focus on multisensor networks and machine learning; and nuclear weapons policy. And in each of these research activities, I engage students and postdocs. So for example, my team currently includes 1 research engineer, 3 postdocs, 5 grad students, a research specialist, and 12 undergrads. So today I'm going to discuss my research through a series of vignettes. First, we're going to talk about understanding nuclear deterrence through war games and implications for nuclear weapons policy. And next, I'll discuss my research applying supervised machine learning to multi-source data from network sensors. And then finally, I'll close talking about research performed at the 8-8-inch cyclotron at Lawrence Berkeley Lab to understand the neutron response of organic scintillators. So here we go. The Trump administration's nuclear posture review called for new types of high-precision, low-yield weapons to provide a flexible option in the nuclear arsenal. And these weapons were deployed earlier this year, and they've long been a source of debate in the international relations literature. Opponents claim that these weapons would be easier to use due to the decreased blast effect, thereby breaking the nuclear taboo and introducing crisis instability by blurring the distinction between conventional and nuclear weapons. Other scholars have touted the potential benefits of these weapons. So because the blast is smaller, there would be less deaths, and then precision targeting capabilities would result in an increased probability of target damage for a given yield. So Lieber and Press, for example, argued that adding these weapons to the arsenal would strengthen deterrence for regional scenarios by providing a more credible threat. And so in doing so, it would raise but not lower the threshold for nuclear use. An example would be in response to Russia's escalate to de-escalate military doctrine. But ultimately, without a means to measure the risks posed by the addition of these weapons to the arsenal, all of these arguments are just opinions. So how do we measure it? Well, thankfully, we have little empirical data on the use of nuclear weapons in warfare, but we can use what data we do have. Formal models like the prisoner's dilemma are useful, particularly in bilateral cases. But these formal models are useful, but they can become challenging when you're trying to consider multiple nuclear armed adversaries, and also including the roles of allies and defense pacts. And computer simulations like agent-based modeling have been used, but these types of approaches require assumptions about the human element. So understanding how humans might respond in different wartime scenarios. And so survey experiments have been conducted to try to understand the human response, but they have posed their own challenges. For example, they can fail to make the situation salient to the respondent because the respondent bears no cost for their decisions. So in 2017, the Project on Nuclear Gaming was established with funding from the Carnegie Corporation of New York to develop a new data generating process for understanding nuclear deterrence. And this is a 2-year multi-institution effort in collaboration with Sandia National Laboratories and Lawrence Livermore National Laboratory, with UC Berkeley as the lead institution, and I've served as the project director for this effort. So through this work, we introduced the concept of an experimental war game, which is a war game executed using experimental principles with the goal of testing a hypothesis. And so the idea is you develop an instrumented war game, which we did using a board and online game format, which is shown here. And then you run it in a controlled treatment experiment. So you set up the game with certain variables, you run it a bunch of times, you change one variable, you run it a bunch of times again, and then you quantify the change in behavior. And this concept was published in Science in late 2018. So our experimental war game, Signal, is a 3-player game designed to represent a nuclear dyad in a multipolar world. So what I mean by that, 3 players, 2 of them have nuclear weapons. There's another country that's controlled by independent human that only has conventional weapons available. So within the game, players interact through military, economic, and political actions. So for example, if you look at the graphic, if you look at this graphic on the right of the slide.
Say sorry, Thea. Okay, Thea. Nick said sorry. It was accident.
Okay. Sorry. Players use signaling tokens to indicate where they want to take actions on the map. And so the signaling tokens are represented by these green symbols here on the hexes, which would parameterize the board, basically. And then they can take actions using different cards. For example, using conventional weapons, they can build infrastructure like towns, they can build military bases, and they can also use nuclear weapons. And so the question we wanted to examine is, how do tailored effects of nuclear weapons, like high precision, low yield weapons, impact the threshold for nuclear use? So we have 2 nuclear armed players, like I said, and in our control group, the players only have access to traditional nuclear weapons. And in the treatment group, they have both the traditional high yield nuclear weapons as well as these tailored effect weapons. And so the game is conducted multiple times, so it's repeatable over and over in the same condition. It's controllable in terms of our ability to vary the weapons capabilities of the players. Game is instrumented. So in the board game, we do this through hosted events with facilitators who will help to collect the data, but don't influence the rules or gameplay because we want to keep the game neutral. And in the online game, data collection is automated. So in addition to tracking player actions, we can also store chat logs, and that can help in understanding the rationale behind player decision-making as well. So let's look at the data. So first, this is a histogram of player actions on the map for a board game data collection event. The different colors in the circles correspond to the country that was taking that action. And the number in the circle corresponds to the number of actions taken in that location. And so what you can see is what you might expect. There's increased action along contiguous borders, in minor states, and at military base locations. So this has plausible, we get reasonable results based on just a qualitative understanding of the data. If we look at it in terms of our research question on whether high precision, low yield weapons increase the threshold for nuclear use, we used a probit regression and looked at the probability for nuclear use in the control and treatment conditions. And so if we compare these populations, what we can see is that we find no statistically significant difference between the likelihood for nuclear use with and without tailored effects weapons present in the arsenal. There are a number of reasons why we might observe such a result. It could be that high precision, low yield weapons don't make nuclear use more likely because there are conventional options that can accomplish the same military end. But there may be game effects as well. The intellectual overhead required to orient to the game is high, and players may not fully understand the effects associated with different weapon types. And also the player pool may impact the results as we draw participants from the general public, and they may act differently than senior military leaders that would be faced with such decisions. This is the kind of, this is a question that we can test because we also collect demographic data and had the opportunity to run the game with folks at DoD and NATO as well. But for me, this project has been a real challenge because it's really difficult to be unable to directly measure the phenomena that you're interested in, and it makes nuclear physics experiments look relatively easy. But we can't say that the problem is just simply too difficult. I think it's too important not to study. And there have also been a number of positive outcomes that have come out of it. Throughout the course of the project, we've published multiple peer-reviewed publications as well as policy-relevant papers. I had the opportunity to manage 7 undergrads and 5 graduate students supported through this project. And the undergrads in particular were responsible for the development of the online game. So that was a pretty impressive feat. And we engaged many more students on learning about aspects of nuclear policy issues through various data collection events, as well as in conference presentations and seminars. And I had the opportunity to engage with the sponsors at the Carnegie Corporation, as well as outside stakeholders at DARPA, DITRA, NATO, and other DoD. So now we're going to switch gears and talk about my work in multisensing. So with support from the National Nuclear Security Administration, we're exploring how low resolution sensing platforms with multiple modalities, multiple sensing modalities, can be deployed in networks at nuclear facilities to characterize operations. This is a picture that shows Oak Ridge National Lab, and each of the yellow dots represent the location of one of our multisensors, the Merlin multisensor, which measures all of these different data products. They're currently deployed there at Oak Ridge, which is around the high flux isotope reactor and the adjacent reprocessing facility, collecting data at a rate of 16 Hertz. We want to use these basic data products to characterize phenomena that would be indicative of proliferation relevant behavior. So things like nuclear reactor power levels or fuel movements. But the Merlins don't have radiological sensors on board. So the challenge is in using these collateral signals to identify the phenomena of interest. And I think it's also interesting that in the kind of pandemic world, the ability to be able to make these measurements remotely, if you think about the challenges that the IAEA is facing in continuing persistent monitoring, while we're doing this for nuclear security applications, there are certainly potential safeguard applications as well. Prior to deploying at the high flux isotope reactor, we did a proof of concept experiment at the 88-inch cyclotron using a similar sensing platform, the Canary, which is shown here. It measures some of the same data products that the Merlin measures. And some of you may have seen Chris Stewart. He's a postdoc in the nuclear engineering department, and he helped to deploy these sensors all throughout the high bay of the cyclotron, in the experimental caves, and around the porch and into the parking lot. The goal was determining whether the cyclotron was on or off using supervised machine learning and basic physical data products. We're going to look at the results today from two data collection campaigns. Indoor, where you can see the sensors deployed inside the building here, and then outdoor, most close to the building, but also spread across the parking lot as well. Here's an example of multi-source data taken at the 88-inch cyclotron. So each of the different plots shows a different sensing modality. So let's just take this one as an example. This is the number of events that we measured with a given acceleration value in cases where the cyclotron was on, which are shown in orange, and in cases where the cyclotron was off in blue. And that same theme follows through each of the different data products here. And so if you looked at the accelerometer data, you can see that if you placed a simple cut on the data to say acceleration values above X correspond to Y, you wouldn't be able to do that for cyclotron operational states. And this is true for each of the different individual data products. The one that provides the most discriminating power is the pressure here. So if you look at low pressure events, these correspond exclusively to the cyclotron being on. But as you look at higher pressure events, again, you have this ambiguity. So rather than looking at each of these data products individually, the question is, how do we use the information in concert to get a better handle on cyclotron operations? Our approach used a feed-forward neural network. The sensor data, shown here, along with the sensor ID, are ingested as inputs. And then moving forward in the network, the weighted inputs are summed and biased. And this value is passed to a function whose output is propagated forward in the network. That process occurs at every node in the network, and the outputs are then passed through to the terminus. The classification assessment by the network corresponds to the class with the higher value at its node. During training, the values at the on and off nodes, for example, are compared to known beam states that we obtained from operator logs. And the degree to which the network has misclassified the observations is used to adjust the weights and biases of the network. This process is iterated until some optimization criteria is reached. The results from the cyclotron data set are shown in this table here. So what you can see is that we can assess cyclotron operations to greater than 90% accuracy from even outside of the building. And then I've also provided the Matthews correlation coefficient. That's what the MCC stands for. This gives you a metric for performance when the prevalence of the labels is unbalanced. So what I mean by that is, if in our training data set where if we have more data points where the cyclotron is on than off, for example, then that can lead to an inflated accuracy, because the accuracy doesn't take into account false positives. So the Matthews correlation coefficient does take into account false positives, and it can be interpreted similar to a Pearson's correlation coefficient in that it ranges from -1 to 1, and the values above 0.7 correspond to a very high correlation between the predicted and the actual labels. So this is a plot that shows the Matthews correlation coefficient as a function of the number of modalities included in the assessment for the indoor and the outdoor campaigns. And these modalities are ranked according to their importance to the classification assessment as determined using recursive feature addition. So there's a couple takeaway messages from this plot. One is that we can generally predict operations better inside the cyclotron compared to outside. But even outside the cyclotron, we're still able to get a very high correlation between the predicted and the actual labels if we're using at least 5 sensing modalities. And we also see that the ability to classify operations tends to increase with increasing modalities up to a point, which speaks highly to the power of data fusion. So if you're looking at these results, you might say, well, that's nice, Bethany, but your magnetic field sensor is your most important sensing modality, and that makes sense because the cyclotron is a giant magnet. So what if you didn't have the magnetometer? Would you be able to say anything at all? So this plot shows the same analysis, removing the magnetometer from the data set. So it's the Matthews correlation coefficient as a function of the number of modalities included. You can see that we still do a better job indoor, but we're able to get high correlation between the actual and the predicted labels from outside the building with no magnetometer. So this is pretty impressive. That said, one of the big challenges with machine learning is that it tends to work great when applied to the other half of the same data set, but it can fail in other settings, even for the same classification task. So going back to the reactor facility at Oak Ridge, what we want to do there is develop a machine learning model using operations logs, and then be able to apply it to an unknown nuclear facility of interest. So the research question is, how do we adapt or fine-tune the model trained at the testbed facility to optimize classification performance at the target facility? And in this case, the target facility for us will be the trigger reactor at the McClellan Nuclear Research Center. So we're using a transductive transfer learning approach. The idea being that you use data obtained at the target facility to inform the machine learning model, even though you don't have labels there. I'll illustrate this with a toy data set. If we look at the top 2 principal components from the target facility data, we can see that they cluster around these 2 regions, but because we don't have labels, we don't know what these clusters correspond to. We can apply that same clustering algorithm to the testbed data set, and there we have operations logs. And so we see that we get similar features, and that this cluster mostly corresponds to the reactor being off, and this one mostly corresponds to the reactor being on. So we can assign each of these data points a cluster ID, that's illustrated here, and we can do that same algorithm on our target data set. This allows us to be able to use a mapping from the testbed to the target data set to assign pseudo labels. And that's illustrated here. And you can feed these back into the trained model that you developed at the testbed facility, selectively freeing these latter layers in the network that are specific to the classification assessment, with the goal of achieving improved classification at the target. These approaches will be integrated into our code base, Mimosas, that enables supervised machine learning using a config file format. So we released this code base as open source earlier this fiscal year. And that's our logo here. This is our website. You can link to our GitHub, and you set it up similarly to how you might set up an MCMP simulation, and just specifying in the config file the number of layers in the network, the number of nodes. And these methods and algorithms are really useful for identifying features and for pattern matching. These tasks are useful for managing large data sets, but also relevant for nuclear physics and nuclear data analyses as well. So let's talk about nuclear physics. The last research segment is on the characterization and use of organic scintillators for fast neutron detection. Organic scintillators are materials that emit light when excited by ionizing radiation. For gamma rays, the recoil particle causing excitation and ionization of the scintillating medium is typically a Compton electron. In the case of fast neutrons, the primary mechanism for light generation in the scintillator is through NP elastic scattering. And so it's the recoiling proton that causes excitation and ionization of the medium. So if we look at a plot of the light as a function of energy deposited, in the case of the electron light, what we can see is it's mostly linear at higher energy depositions, but that's not the case for the proton light. The shape and magnitude of the proton light yield relation depend upon the scintillating medium. There's currently no physics-based model of the proton light yield curve. So if we want to know the neutron response for different organic scintillators, we need to measure it. And we do that work at the 88-inch cyclotron at Lawrence Berkeley National Lab. Deuterons are produced in the cyclotron and steered through a series of bending and switching magnets to a breakup target in the cyclotron vault. And that's shown here and here. So deuterons are impinged on the breakup target. Neutrons go flying in the forward direction. They're collimated by 3 meters of concrete and 1.5 meters of sandbags. And what results is a broad spectrum open air neutron beam where we can place our scintillators in this experimental cave there, and we can make our measurements. So in addition to characterizing the scintillators themselves, we can also use them for neutron time of flight spectroscopy. And that's what's illustrated in this plot here. So this shows the number of neutrons per microcoulomb per steradian per MeV as a function of neutron energy for a 16 MeV deuteron beam on a beryllium breakup target. And this work was led by an undergraduate in my group, Keegan Herrig, who is now a graduate student at UC Davis. So what's neat about the cyclotron neutron source is that we can tailor the spectrum using different incident deuteron energies and different breakup targets for different applications. So now let's look inside the experimental cave. The neutrons are emitted through a Kapton window here at the beam box, and they impinge upon this target scintillator that we want to characterize. We can determine the incoming neutron energy using time of flight. So in the target scintillator, the neutrons undergo NP elastic scattering, and we have a number of different observation scintillators at forward angles with respect to the target, where we can detect the scattered neutron. That's shown here. We can determine the energy of the scattered neutron using time of flight between the target and the observation detectors. And we know the angle of scatter of the neutron because we placed the scintillators there and we know where we put them. This gives us the kinematically over-constrained system for measuring the proton light yield, which means that we can calculate the proton recoil energy on an event-by-event basis 3 different ways. And the result of this measurement is a continuous determination of the proton light yield over a broad range of energies in a single measurement. I developed this double time of flight technique with Josh Brown during his time as a graduate student at UC Berkeley, and have since grown this program across multiple sponsors and application areas. And so now I'm going to give you an example of some of that work. This is an example of my work with Sandia National Laboratories through the single volume scatter camera project. So the idea is that you're doing neutron imaging, and it's similar to the concept of Compton imaging, where the neutron image is produced through kinematic reconstruction. In the single volume concept, the goal is to detect multiple neutron interactions in a single volume. So the neutron comes in, it undergoes an NP elastic scattering event, and then within centimeters of distance and within nanoseconds in time, it interacts again. Using the position and time of these interactions, you can determine the energy of the scattered neutron. And you can see from the kinematics equations here that in order to get the energy of the incoming neutron and the scattering angle, you also need to know the energy of the recoil proton. But what you measure is the scintillation light. And what relates the light back to the proton energy is the proton light yield relation. So we were subcontracted to obtain the proton light yield relation of various plastic organic scintillators that are candidates for use in the single volume scatter camera. So what's shown in this picture here, just some examples of plastic organic scintillators from Elgin Technology. And we looked at a number of these. First is we looked at the EJ200 series. So this is EJ200, 204, and 208. And this is a plot of the light yield as a function of proton energy for these three materials. And so what you can see here is that the results agree within error. And what's neat about this work too is that we were able to extend the proton light yield measurement down to 50 keV, which is a new low energy limit for these materials. You can also see that in addition to them agreeing with each other, they also agree with experimental determination of the EJ200 proton light yield from Zhang. This work was led by Thibault Laplace, who was a postdoc in my group and is now a research engineer. And we did this several years ago, published through the SORMA conference proceedings, but it just got bibliographic details this year. And here's another example. We also looked at the EJ230 series. So this is EJ230, 232, and 232Q. The reason we're looking at all of these different materials is because each of them have different electron light yields and different temporal responses. So they each bring different opportunities and challenges for the single volume scatter camera. So again, here's a plot of the light yield as a function of proton energy for these three materials. And you can see that again, they each agree with each other. And it turns out they also agree with the measurements from the EJ200 series, suggesting that the primary mechanism for ionization quenching in the scintillator is in the solvent, as these all share the same polyvinyl toluene based material. And this work was led by Juan Manfredi, who is a postdoc in my group and was recently published in IEEE Transactions. Under a separate project led by Edith Beret at Lawrence Berkeley Lab, we were contracted to examine the performance of novel scintillating materials and compare them to commercial standards. A new organic glass was developed at Sandia National Laboratories that has a high electron light output and pulse shape discrimination properties, meaning that the temporal response of the scintillation light can be used to distinguish different types of incident ionizing radiation. We compared the organic glass performance to PSD commercial standards, EJ309, which is a pulse shape discriminating liquid, and EJ276, which is the only commercially available pulse shape discriminating plastic. We measured the proton light yield of these materials, but I'm not going to show that. We also looked at other properties. So this is just for illustrative purposes. We looked at the relative electron light output. So if we expose these scintillators to gamma rays, which one is going to give the most photons for a given amount of energy deposited? That's what you're looking at here. This is the counts as a function of integrated charge, where each of these scintillators is affixed with the same phototube, same bias voltage, incident with a cesium-137 source. And so you can see that the organic glass is much brighter than, for example, the EJ276, and even brighter than the EJ309, which is the standard for many applications. We looked at the pulse shape discrimination properties of these materials. This is a figure of merit, which is commonly used to describe the discrimination performance as a function of proton energy. What you can see here is that the organic glass tends to have pulse shape discrimination performance similar to that of EJ309 and much better than that of EJ276. So while, for example, both the EJ309 and the organic glass show good separation down to 600 keV, the EJ276 lacks clear separation below 1 MeV proton recoil energies. This work was also led by Thibault Laplace, and we just submitted it for publication last week. So I'm really excited about that. Here's another application-driven example of our proton light yield measurements. For a project led by Professor Gabrielle Orebigon in the physics department at Berkeley, who's also a faculty scientist at Lawrence Berkeley Lab, we're measuring the proton light yield of the water-based liquid scintillator, which is a candidate material for use in antineutrino detectors for nuclear reactor monitoring applications. So this picture on the left shows an example of a nuclear reactor facility in Iran that may be of interest for this type of technology. The Watchman experiment aims to demonstrate the capability for remote reactor monitoring via antineutrino detection at a standoff distance of 25 kilometers. So the Watchman or a Watchman-like detector will be built in the Bulby lab in the UK, which is 25 kilometers from the Hartlepool nuclear reactor. Fast neutrons form a background for this rare event detection, looking at the antineutrinos from this reactor, so we can inform the modeling and simulation of the performance of, for example, water-based liquid scintillator in a Watchman-type detector through proton light yield measurements. The plots on the bottom of the slide here show the relative light yield as a function of proton energy for the water-based liquid scintillator and for LAB PPO. This is linear alkyl benzene with a wavelength shifter that has previously been measured, and it will serve as a fiducial for the analysis. Recently, we also demonstrated the capability to obtain the carbon light yield of organic scintillators. So in addition to NP elastic scattering, the neutron can also elastically scatter off the carbon, resulting in a recoiling carbon nucleus, which again causes excitation and ionization of the scintillating molecules. NP elastic scattering is constrained to forward angles, but if we place observation detectors at backward angles, we can observe the light from the carbon recoils, again, on an event-by-event basis. And that's what's shown here. So we're in a different experimental cave at the 8.8-inch cyclotron. This is cave 5. Neutrons are coming in here. This is our target scintillator, and you can see our observation detectors at both forward and backward angles. And here's a plot of our preliminary results. So this is the light yield as a function of recoil energy for both protons and carbons. So this is the first continuous measurement of the carbon light yield of organic scintillators, and it's also the first in situ determination of both the proton and carbon light yield in a single measurement. These data are important for the design and development of new neutron detection systems. And we can also use the relative light output of the proton to carbon recoils, where we avoid systematic biases in measuring these in independent measurements, to understand more generally about ionization quenching in organic scintillators. So I'll tell you more about what I mean by that here. I mentioned earlier that as a community, we don't currently have a good physics-based model of ionization quenching. This is a plot of the light output as a function of proton recoil energy for EJ309, which is a liquid organic scintillator, the red show experimental data. This was not our work. This was from Norsworthy. And then the black curves represent different empirical and semi-empirical fits to the data. So what you can see from this is that in the region where they have data, the curves all line up nicely. And in the extrapolation region at low energy, they diverge wildly. So which model would you want to use? Often in the community, folks rely on Burke's as the standard. So this is just to give you an idea of what these models look like. This is the parameterization of the Burke's relation. So this is the the differential light output as a function of distance traveled of the particle in the medium is equal to the scintillation efficiency times the stopping power divided by 1 plus some quenching parameter times the stopping power. In the case of the Norsworthy measurement, what they did was they used the Burke's fit that they obtained from the data in a simulation to simulate response functions. They compared this against their measured response functions and concluded that the Burke's model provided the best fit. But our recent measurements of low energy proton light yield allow us to use data in the region below 1 MeV to constrain these models down to 50 keV. This is a plot of the light yield of EJ309 as a function of proton energy. And the data here are fit with various semi-empirical and physics-based models. The Burke's model is shown in red. And what you can see is that we can reject this model at energies below 1 MeV. Right now, both the Camlin and the Volts model, it's hard to see, but both the Camlin and the Volts model are in good agreement with our data, so we can't distinguish these. But the new carbon light yield data will allow us to get a better handle on these models because we have the measured ratio of the carbon to proton light yield. And if you look at something like the Burke's relation, many of these models are similar in that the only thing that changes for the different recoiling particles is the stopping power. And so for a good model, we should be able to constrain these fit parameters, change the stopping power, and continue to be able to describe the phenomena that we measure. And so from there, perhaps we can recommend a model of ionization quenching, or if needed, develop our own to improve our ability to extrapolate the measured data to these lower energy regions, which are of interest for a wide range of applications. So in closing, I've shown you a broad range of research activities in applied nuclear physics, data analytics, and nuclear weapons policy focused on reducing the risks posed by nuclear weapons and related technologies. And I've talked about my role in developing students and postdocs in the laboratory, as well as a contributor and leader of various scientific research programs. Moving forward, I'm excited by the prospect of expanding my role in the UC Berkeley campus to train students in the classroom, as well as my work at LBL through experimental studies in low energy nuclear physics. Before I end, I want to acknowledge the contribution of a large number of students and postdocs. And I failed to modify the slide, but I need to also recognize Professor Gabriela Rebigon in collaboration on the water-based liquid scintillator, as well as her graduate student, Ed Callahan, and collaboration with a large number of lab scientists. And I want to thank the sponsors for their support of this work, and thank you for your time and attention.